All right, so today we'll pick up where we left off yesterday and talk about the extreme value theorem. And then we'll begin talking about derivatives. Okay, so remember the example we were working with yesterday with the extreme value theorem was the function 1 over x. Right, and we just cared about x being in the interval 0 to infinity, so that we didn't have to worry about the discontinuity at 0. I feel like the domain problem is 0. And what we concluded is that on this interval, this function takes no maximum value. And similarly, it takes no minimum value. The problem was, okay, as you got close to 0, this thing just keeps going up, up, up. And as you head out towards infinity, this thing keeps going down, down, down. But it never stops going down. It never hits 0. It just keeps approaching 0. So we have limits in either direction, but it never actually attains that limit. So there is no maximum or minimum value on this interval. The extreme value theorem is going to give a criterion for when we can find a maximum or minimum value of a function on an interval, at least if our function is nice enough. And you won't be surprised to find out that the condition that we need for the function being nice enough is what? Continuous, right? We need continuity. That's everything in this class, right? The answer is usually going to be continuity. We need at least continuity. All right, so let's let f of x be a continuous function. Now we're actually going to need a second hypothesis. It's going to be on an interval, but we already saw, 1 over x is certainly continuous on this interval. Right? There's no problem there. But it doesn't hit the max or the min, and the reason why is because we don't include the endpoint. We have an open interval. If we have a closed interval, we can get rid of this problem. So we're going to have a continuous function on a closed interval. We'll just give it a name. We'll call it AB. Okay? So we really include the endpoints. And you can see what happens if we stop this function somewhere. We've got our A, and we stop the function over here, and we've got our B. Well, now it really will attain a maximum value. Right? At this point, you get a max, and at this point, you get a minimum value on that interval. And it's all because we include the endpoints. If you don't, right, you can just arbitrarily get closer and closer and have it go up, 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 but it doesn't hit that endpoint, so it never hits a maximum value. Okay? But once we use a closed interval, we're okay. So, if we have a continuous function on a closed interval AB, then there exists let's say points C max and C min in this interval AB. Okay, so two different real numbers. I just call them C max and C min, such that f of x, well, let's write it like this. Let's say f of d, let me start, C min. If I apply this function at C min, I want this to be the smallest possible value of f on that interval. Okay? So the way I'll write it is this. F of C min is always going to be less than or equal to f of d for any d in the interval AB, and f of d is going to be less than or equal to f of C max. Right? And this is for all d in the interval AB. Okay, so this is just some mathematical way of writing it down. But The idea is the important thing here. And what's the idea? There is some point where it gets to max, and there is some point where it gets to minimum. Right? This function shows you if you don't use the closed interval, it's not going to work. Right? And what happens if we throw in the other side of this function? Right? It's not continuous at 0. And let's say instead of going all the way to infinity, let's just use a closed interval. Let's say -2 to 2. Okay, so now we really have a closed interval. Okay, so we'll put that'll be -2, and that'll be 2. Okay. On this interval, does the function take a maximum value? No, it still shoots up, right? Does it take a minimum value? No, it still shoots down. So just having a closed interval isn't enough. Okay? Continuity is important, right? We don't have that the function is continuous at 0, because it's not even defined there. Okay. So both of these hypotheses are needed. Okay? And one can prove, and we won't, but one can prove that this is enough to guarantee that you will get a minimum value and a maximum value. Okay? All right, now let's make a totally trivial, dumb observation. Totally trivial, dumb observation. Where can the maximum value, for instance, occur? Well, let's keep this point C max. Right? C max is either in the set A, B. All right, so it's either one of the endpoints, or, actually the word either here is inappropriate. Could be both. Just say C max is in the set A, B, or C max is in the interval AB, where we don't include the endpoints. In other words, the point where the function is going to take a maximum is either one of the endpoints or it's in the middle. Okay? There are no other options. That's why it's totally trivial. Right? You're either on the ends or you're not. Okay. Fair enough? You're either on the ends or not. Now, this is a wonderful finite set. It has 2 elements. It is very easy to check a function at 2 points. In fact, I bet a lot of you, when I give you a function and I say graph it, you immediately write down some table and start plotting points. Okay? And usually even use more than 2. So you're used to plugging in points. So the extreme value theorem says half of your job, if you want to find where the max is just to evaluate at these 2 points and check. Okay, see what value you get. So you're used to doing that, no problem. Okay. What about this? If you have an interval A to B, and let's assume A is really smaller than B. How many points, right, lie between A and B on the number line? Infinite, right? There's lots and lots of points in between here. If I told you to check the function in each one of them, you say, okay, that's going to take me quite a while. You're going to give me more than 6 points on the homework if I do that. Okay? So this is a lot to check. So we want to come up with some sort of shortcut for checking all those points at once and figuring out what the function is doing. That's where calculus is going to come in. Okay? So this part, this is plug and chug. And this part, this is the calculus part. Okay. So, in not so many lectures, you're going to see how I can give you some interval and say, find the max of this function on the interval. Right? And you're going to use calculus to determine whether or not the maximum is somewhere in this middle, right? Or in one of these 2 points. And of course, whether it's on one of these 2 points is easy. You just plug this in and check, and then see what the max is on this interval, and compare the two. Okay. So later on we'll see examples of using this. And incidentally, everything I said here with C max, right, is the same with C min. Right? The minimum is either going to occur on an endpoint or in the middle. Right? And calculus again will tell you what the minimum is going to be in the middle, and plug and chug will tell you what it is on the endpoint. So you just compare it. Okay? At this point, it's hard to apply this theorem because you don't know how to find the max or the min of a function here. Right? All you can do is this right now. So that's okay. We all start ignorant. I mean, some are more ignorant than others. Not to name any names. No, not you, Steph. No, the one behind you.
I don't.
Okay. Any questions? Okay, I know I didn't even show you an example of using this yet, okay? Because we have to get that to really see it in action. But intuitively, does it make sense what's going on? Yeah? Good. Okay. Then we can start talking about derivatives, which is, right, this is the cool part of the course. Okay, so let's remember the first lecture, right, this big picture lecture. We talked a lot about functions representing the velocity, or the position, right, of some object moving through space. And we said we wanted some way of measuring the velocity at any given point, the instantaneous velocity. And we remembered that, okay, if you had some curve, and you picked a point on that curve, and you said, I want to know how fast I'm going at that point. Right? So if this was my position, right, how fast am I going as I'm moving? We said, well, okay, we could draw another point and draw a line connecting these 2 points. And what was that line telling us? Slope. Well, it's a line, it has a slope, and what does that slope tell us?
The rate of change.
It's the rate of change, but right between these 2 points. Okay? Right? And of course, all that's saying is, well, okay, if this is a point A, and this is a point, well, sometime later, call it h later, then over here, this was giving us f of a, and this over here is giving us f of a plus h. Okay. Then what is the slope telling us? Well, slope is rise over run. Okay? And remember, this is supposed to be some sort of a position function. So this here is your position, this here is time. Because they use s of t. So this is how much your position changed. Right? And this distance, the run, is how long it took you. So how far you went divided by how long it took you. That's exactly your average velocity over that, right, over this interval. Okay, no problem. So this line we call the secant line. And secant lines give the average velocity on an interval. Now that is the slope of the secant line does. So the slope of the secant line through, well, the points are a, f of a, and a plus h, f of h, f of a plus h. So the slope of the secant line through these points gives the average velocity, right, between these 2 points, okay? Okay, no problem. Okay, so you get this nice line. Okay, the next thing we did is we started moving this point closer and closer to this point A. All right, or equivalently, we started making this h smaller. Okay? So we had this equation for the slope. Okay, this is our average velocity. And we start moving this h towards the point, making the h here smaller. By the way, this, of course, equals h on the left. And as you move it, right, let's say you move it down to here, you can see that, right, the slope of the line can change considerably. Right? What does that tell you? Well, that tells you that this original estimate of how fast you were going at this point is not a good one. Okay? And that should make some sense to you. The farther away your second point is, the worse estimate you're probably going to get. Okay? And the closer you bring it, the more likely your average velocity is going to be closer to your instantaneous velocity. Fair enough? Okay? Fine. So as we start getting this closer and closer, right, the line that we get, right, is moving and moving, but what we hope is that it actually starts to converge to something. Right? That is, it gets closer and closer to some target. Okay? And of course, when I say target, what word are you thinking?
Limit.
Limit, right? They're kind of synonymous in this class. Okay? And so what we want to know is there a limit as h goes to 0? Okay? Does this average velocity start to target some fixed velocity, right? Which is the instantaneous velocity. And that's what would happen, right, if you put the second point right on top of the first point. Okay, of course, we're not allowed to do that, right? We're not allowed to put the second point right on top of the first point. Why not? Well, you can't divide by 0. Why does that make the limit so good? Well, because the limit doesn't let you put 0 in for h, right? It is set up, the limit is set up to solve this problem. Okay? It's something specifically designed to look at what it's getting closer to, but never actually allowing this h to be 0. Okay. So let's see how we use it. So first we give a definition. Let f of x be the function and a real number. F of x is differentiable at x equals a if the limit as h goes to 0 of f of a plus h minus f of a over h exists. Now, we've already seen that limits sometimes don't exist. Okay? So it's possible that a function is not differentiable at a. I'll give you one very simple example. Assume a is not even in the domain. Then, of course, this f of a doesn't make sense. So this limit doesn't make sense. So the limit doesn't exist. So f isn't differentiable at a. So for instance, f of x equals 1 over x. Is it differentiable at 0? No, right? 0 is not in the domain of f. You can't even, this limit doesn't make any sense because that doesn't make any sense. Okay? Okay, very good. Also, this is a two-sided limit. That's important. Right? When do two-sided limits exist? When what are both equal?
Limits.
Which limits?
Both sides.
Exactly, the one-sided limits. Okay? So, strictly speaking, if you're trying to be careful, you have to compute both the left and the right limits and make sure that they exist and that they're equal. Only then will this two-sided limit exist, right? And then you can say it's differentiable. Okay? So, if this limit exists, we call the limit the derivative of f of x at x equals f. I don't need a comma. And we write, so the most typical thing that I'll write is I'll call this f prime of a. Right? This means the derivative of f at a. And this is just by definition. It's just this quotient. So this is, that's the definition of the derivative. Okay. So next time, which will be tomorrow, we're going to take all these properties that we had about limits and continuity. Remember we had these kind of 6 properties that we put up? And we're going to rewrite these for derivatives. Right? Because somehow if you define things in terms of limits, you'd expect those sort of properties to carry through. Some of them will, and some of them will require a little bit of tweaking. Okay, but today let's just compute a few without worrying about rules. Just do a little bit of algebra. Okay, so let's pick a function. Let's do negative 3x squared plus 2. Just to pick one randomly. And let's look, well, let's call it A. Somebody pick a nice real number. Something not too horrible. What?
3.
3, okay. So we're going to see if this function has a derivative at x equals 3 and figure out if it does have a derivative, what it is. So we have to look at this limit. We're going to look at, okay, a is 3. Okay, well, what do we do? Plug it in, right? We have a function, we have some values, right? We just got to fiddle with it. So let's see. All right, so f of 3 plus h. That means everywhere you see an x, you have to put a 3 plus h. So I get negative 3, 3 plus h squared plus 2. Okay, that's the first part. Okay, so this whole bit corresponds to f of 3 plus h. And then I have to do minus. Oh, this is nice. I just evaluate f at 3. Even the most dim-witted individual who's graduated from 7th or 8th grade can do that. Let's see. 9 times minus 3 is minus 27. Plus 2 is minus 29. Minus 25. And I divide by h. Very good. Okay, and we continue just to do algebra. The trick here is to hide all of the tricky stuff in this limit, which we feel comfortable with now after spending a good week or two with it. Okay? Everything else we're doing, just algebra. Nothing to be afraid of. It's all good. Okay, so I need to expand a bunch of stuff here. So let's see. Okay, if I have, let's put the formula on the sideboard for a second, just so we all remember. You take x plus y and you square it. This is x squared plus 2xy plus y squared. Yep. So we just apply that here and say, okay, 3 squared is 9. Okay, so I'll just minus 3 out here. So 9. And then plus 2 times 3 times h. That's 6h. Plus h squared. Okay, and then we add 2. And then, well, this is going to be minus 25, which is plus 25. And we divide by h. Okay, so let's see. Now, if we're clever, we can do some of this in our head. Minus 3 times 9 is 27. But on the end, you have 2 plus 25, which is also 27. So the minus 27 and the plus 27 cancel out. And so all I'm left with is 6h plus h squared over h.
How did you end up from -3 all the way around?
Oh, good, you caught me. Okay, so I can't just forget about the -3. I got to multiply that into everything. Okay, fine. So -3 times 6h is -18h. And -3 times h squared is -3h squared. Okay, so you guys are all experts on what to do with limits that look like this now. Okay? We've been doing homework problems on it now for a week, so what am I going to do?
3h. I'm
What
going to take 3h out.
You're going to take 3h out?
No, h squared out.
Take h squared out.
Just
No,
H.
and
Oh, yeah.
Okay, well, let's try h. Then maybe we'll try h squared. Okay, so we'll take an h out of the top, and I get -18 minus 3h, and I divide by h. Okay? H is going to 0, but we never allow h to be 0. Right? That's what we do when we take a limit. What does that mean? That means I can cancel these h's. Right? I'm not dividing by 0 when I do that. Okay, so I'm left with the limit, as h goes to 0, of -18 minus 3h. Right? And while I don't allow h to be 0, I do allow it to go to 0. And as it goes to 0, minus 3h goes to 0. And I'm just left with -18. Okay, so the limit exists. It's -18. And so we could say that the derivative at 3 is -18. Which tells us that if we graph this function, right, and what's the graph going to look like? All right, your mind should be doing the Mathematica thing now, and you're going, okay, wait, x squared is 2, and 3x squared doesn't really change it a whole lot. Minus x squared makes it go down, and then plus 2 makes it go up. Okay, so now you got the graph in your head, right? Okay, so let's graph it. Okay, so let's see. X squared went like this. 3x squared just makes it a little thinner, right? Minus x squared flips it around, and then plus 2 makes it go up plus 2. Just like that. Okay, let's see. Now at 3, we'll just plug it in really quickly. We said, oh, actually, we did plug it in, right? And we got, hey, did I put in, yeah, good, -25. So it's supposed to be -25. So if you put in a 3, then it's way down here at -25. Right? Okay, fine. What did the derivative tell us? Well, it said that there is a line hitting this graph at that one point, and the slope of this line equals the derivative at 3. So this is our f of x. Okay, and of course this is now minus 18, right? Which you would believe from this graph, right? Minus 18 is the slope. It's a pretty steep graph. So you now know what, if you drew this line, which represented the velocity, the instantaneous velocity at that point, it would have slope minus 18. Okay? Let's take it one step further. Okay? The slope of the, and by the way, this line here is called, as opposed to the secant line, this is called the tangent line. Exercise for home. Figure out why the secant line is called the secant line and the tangent line is called the tangent line, and it has anything to do with trigonometry. So the slope of the tangent line to the curve f of x at x equals 3 is minus 18. Okay, so we have a slope. But we also have a point. We know it hits the graph right at that point, and that is 3, negative 25. Okay, we have a point and we have a slope, so we can use point-slope form. So, okay, the point, let's see, y minus 25 becomes y plus 25 equals the slope, minus 18, times x minus the x-coordinate, which is 3. Okay, we'll rearrange. So y equals negative 18x. Now let's see here now. What's 18 times 3? That's 54. You have minus 54. Then you're going to subtract 25, so it's minus 79. Is that right?
No.
No.
That's possible.
Ah, because I did minus, and minus is a positive. Did you guys ever see Stand and Deliver?
Yes.
If you have not seen it, it is required for this course to watch it. It's an 80s movie about a math teacher named Jaime Escalante who went in and taught some inner city LA students calculus.
I saw that.
Yeah.
Excellent movie. Excellent
It was a
movie.
good movie.
And he tells them at one point, a negative times a negative equals a positive. Say it! A negative times a negative equals a positive. There's also a very cool trick that you can only see in the background of that movie that I'll teach you guys next quarter, that I learned from watching the movie. Just in case you didn't think you could learn math by watching TV. Okay, so let's do this again. All right, that's 54 minus 25. So that's 29. All right, let's see. 54 minus 25. Okay, we're going to make that a 4 and carry the 1. 14 minus 5 is 9. 4 minus 2. 29. Okay, very good. Okay, so this is, well, the equation of the tangent line. That's pretty cool. Okay. If somebody said you have a nice curve, and here's a point on the curve, and I want you to tell me not only the velocity at that point, but I'm going to draw a tangent line to the curve with the slope equal to the velocity, and I want you to tell me the equation of that line, this would seem utterly ridiculous if you didn't know that it was just simply a little bit of calculus. It's not all that hard calculus either. Okay, let's do something else with the same example, because somebody made a comment that when we got to this point, we should divide by h squared. So let's see what happens, just for fun. I mean, what if we got a different answer? That would really mess things up for us mathematicians, don't you think? All right, so let's see. We got to here. That's when we were worried. Okay, so the limit of h goes to 0 minus 18h minus 3h squared over h. Okay, and we want to try factoring out h squared on the top. Now, part of the reason you want to do that is because when we had limits going to infinity, that's exactly what you were supposed to do, right? Take the highest degree term on the top, highest degree term on the bottom, factor them out and cancel. Okay. Let's see what happens if we try that in this situation. So I'll factor out an h squared, and I'll get minus 18 over h minus 3 over, well, I can't do much. I have to make it an h. Okay. Now I cancel the h's. Let's see. So I get rid of one h, so I have h times minus 18 over h minus 3. And of course, there's no over anymore. Okay, and now you might think, okay, well, let's see. H goes to 0. That's going to go to 0. And what's the problem? It goes to 0. Distribute it. Okay, let's distribute it. Okay, so I get minus 18 minus 3h. Oh. Look at that, you get to the same place. Okay, so turns out in this case, it doesn't matter what you do. This trick works. Again. So the answer is you're both right. I can't remember who both of you were. It's not so important. Nobody worries about taking credit in this class except me. Okay, let's do another example. Okay, let's do an easier one. I mean, easier ones are fun. Okay, f of x is equal to c. C is some real number. Okay, now, those of you with pre-knowledge, which if you recall is the word I use for those of you who've taken calculus and already know some of these tricks, those of you with pre-knowledge, tell me, what will be the derivative of this function at any point?
0.
0. Okay, so I pick any. I love that delayed 0. Interesting. Okay, so a is some point, right, and I want to know what is the derivative at a. Okay, and the claim is that this is 0. Okay, so we prove it. Well, we know that this is equal to the limit as h goes to 0 of f of any for any a, f of a plus h minus f of a over h. Okay, and this is equal to the limit as h goes to 0 of what? Well, f of a plus h. Everywhere I see an x, I have to put an a plus h. Okay, I do that. There are no x's, so I don't have to do anything, and I just get c. It's a constant function. Then minus f of a. Again, that's c. And of course, c minus c is 0. And so this is the limit as h goes to 0 of 0 over h. Okay? Now, as h goes to 0, this goes to 0 over 0, right? What happens at 0 over 0? Uh-oh. You guys told me it was always 0. What's going wrong here?
0, 0, 0.
No. Or they don't collide or split it.
I can't do that. I'm on camera. What's going wrong here? Why am I stuck if I go 0 over 0 and then I'm stuck? What am I doing wrong?
Dividing 0 over h is a 0, isn't it?
What's that?
0 over h is a 0.
0 over h is 0, except if h equals 0.
Right.
And aren't I taking h to 0?
No,
But you're only
really
finding what
close
the
to it.
limit. You're not finding the. You're not really using that 0.
Boom. Boom. Well, the limit says get really close, never actually put 0 in. Okay? As long as this is not 0, then I just have 0 over something not 0. It is 0. So this is equal to the limit as h goes to 0 of 0. And now there's no h's, so we know what to do with these limits. That's a property, I don't know, I think it was f. This is 0. Okay, so your pre-knowledge is correct. Okay, so now, in this case, the fact that we put some a in here is completely irrelevant. Right? We got the same derivative no matter what. When a function has, well, not necessarily the same derivative no matter what, but we know that the derivative will exist no matter what, then we're going to give another definition, just a broader definition. And we're going to say the function is differentiable without saying at x equals a. So let me say it in two different ways because we may use them in different places. So actually, I just do it in one way. I like being short. A function f of x is differentiable on an interval I if it is differentiable for every point A in I. Okay, so this is just a, okay, if I know my function is differentiable here, 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 everywhere on an interval, then I'm going to say it's differentiable on the interval, not just at a point. Yeah.
Random question. That e there between the a and the I. What exactly does that mean again? Yeah.
Okay, so on the left is always an element, on the right is always a set, and this means is an element of. Okay, so this is an element of that set. Okay. So if I is the interval from, say, 0 to 10, then I'm saying here A is some number between 0 and 10. Okay? And, well, this, in general, when I use this set doesn't have to be an interval, it could be any set. I'm just saying this is some element of that set. Good question. Okay, so a function is differentiable in an interval if it's differentiable at every point in that interval. Okay? And if a function is differentiable for every point in its domain, we call f differentiable, or f of x differentiable. And we just don't put any qualifier on the end. So it's like continuity, right? We said if a function was continuous at every point in its domain, we just called it a continuous function, right? Like a polynomial, right? Polynomial is continuous everywhere, so we just say it's a continuous function. Same thing's going to work with derivatives. Okay? If a function, everywhere it's defined, the derivative exists, we say the function is differentiable. So again, for example, polynomials are differentiable. Okay? But of course, that always means you can go backwards and say, okay, if it's differentiable, then it's differentiable on an interval, and it's also differentiable at every point. Okay, so we've run out of time, but let me just say one last thing, which is next time we are going to show why continuity is so important to derivatives. Namely, every differentiable function is already continuous. Right? This limit definition implies that. Okay, and then we'll get into all the fun rules. So, have a nice afternoon.